Greetings to all my colleagues and fellow lecturer, Dr. Rose. I'm Andrew Wing. My teammate Tanishwari, Aaron, and Gokulan are here to present you the topic of material, properties, and manufacturing process of making crankshaft. First of all, we all know that crankshaft is very necessary in engine combustion. Therefore, the material selection is very important. Therefore, I would like to highly suggest steel and forged iron. Next, for the manufacturing process, I will go for forging process. It is the process involving the shaping of metal through hammering, pressing, or rolling. Next is casting. It involves or using to create a mold, which will be used to form the crankshaft during casting. The mold is typically made of sand or another refractory material that can withstand the high temperature involved in the casting process. Tanishwari will explain more in details about the manufacturing process in upcoming slides. Allow me to explain why steel and forged iron is suitable for crankshaft based on the physical and mechanical properties. Steel offers high tensile strength, making it capable of withstanding the significant force and stresses experienced by crankshaft during engine operation. Steel can be high-treated to achieve the desired hardness, ensuring the crankshaft can withstand wear and deformation over time. High wear resistance is an essential property for materials used in making crankshafts due to the nature of their function within an engine. The crankshaft is subjected to continuous rotational motion and cyclic loading, which leads to frictional wear at contact point with other engine components, such as bearing and connecting rods. For mechanical properties, steel used in crankshaft typically exhibit high tensile strength to withstand the force experienced during engine operation. It's essential for steel used in crankshaft to have a high yield strength to resist permanent deformation. Hardness is the resistance of a material to deformation, indentation, or penetration. For crankshaft, high hardness is desirable to resist wear and deformation at contact point with other engine components. Next is the physical properties and mechanical properties of forged iron. For physical properties, the melting point of iron is approximately 1538 degrees. Forged iron typically has a dark gray color. Iron is ferromagnetic, meaning it can be magnetized. For the mechanical properties, forged iron exhibits high strength, making it suitable for withstanding the high stresses and loads experienced by crankshaft during engine operation. Iron has good toughness, meaning it can absorb energy without fracturing. This property is important for components like crankshaft, which experience cyclic loading, while iron is susceptible to corrosion. Forged iron components can be coated or treated to enhance their corrosion resistance, depending on the specific application requirements. With that, it's the end of me presenting my part to everyone. I will pass down to Tanishwari to continue the presentation. Thank you.
Hi, Doctor. I'm Tanishwari Subramaniam. I'm the one of the group member for group number 3. So this is my presentation slide. Okay. So for the manufacturing process, there are two processes, which is fogging and casting. Before that, I want to briefing a bit for crankshaft. Crankshaft in the automotive and aerospace industry, crankshaft play a crucial role in transforming the reciprocating action of pistons into the rotational motion that drives our machinery and cars. Fogging and casting are the two main manufacturing procedures used in the creation of these complex items. Fogging process is process of using compressive forces to shape metal. When it comes to crankshaft, a temperature fogged steel blank is formed using a number of dies to give the crankshaft the correct shape. The next one is casting process. Casting process metal is poured into a mold during the casting process to generate the desired shape. When it comes to crankshaft, the shape is created using a metal die or sand mold. The crankshaft shape is formed by pouring molten metal into a mold and letting it cool and harden. This is the fogging process, step by step. There are 3 steps for fogging process, which is heating, the second one is shaping, and the third one finishing. Heating a steel blank to a high temperature, typically between 1100 and 1300 Celsius. This is the first step in fogging process. In order to prepare the metal for shape, this technique softens it. Shaping. Crankshaft is shaped by applying enormous compressive stresses to the heat blank as it is positioned between a sequence of dies. The third one is finishing. The crankshaft is subjected to further machining following the fogging process in order to obtain the final dimensions and surface polish needed to accurate installation and best performance within the engine or machine. This is the casting process. There are 3 steps for casting process. The number 1 is mold preparation. In order to accurately capture the complex geometry of the crankshaft, a mold either made of metal or sand must first be carefully designed and created. The second one is pouring and cooling. The prepared mold is filled with carefully poured molten metal, usually steel or iron. Cooling and solidifying the metal becomes the precise shape of the mold. The third one is finishing. Crankshaft could need extra machining after casting in order to assure exact measurements, smooth out any defects, and trim away any extra material. So these are the function of casting and fogging, and there are steps for fogging and casting with explanations. Thank you, Doctor.
Good evening, I wish to my fellow teammates and my lecturer, Dr. Rose. Today I am going to present my part for this engineering task, which is task C. Okay, the topic I am going to explain is about HB plot, which is data that we use to select materials. As you can see here, this is the diagram that I was mentioning before. HB plot. The HB plot above shows a bubble graph of toughness over yield strength or specific property like fracture toughness versus density. HB plot illustrates the relationship between yield strength and fracture toughness for different engineering materials, showcasing the indicated by diagnostic, which is equal to Kc fracture toughness or yield strength versus density. HB plot illustrates the relationship between yield strength and fracture toughness for different engineering materials, showcasing the mean steel as the most highest fracture point, and as you can see here, the lowest will be silicates, oxide glasses, and those are non-metal side materials.
Hi everyone, I will talk about the possible costing. Our case is forging iron versus casting alloy steel. The case study will be based on a 1.6 liter 4-cylinder engine's crankshaft. Crankshaft weight assumed at 26 kilogram. Cost of iron per kilogram is at Malaysian ringgit 6. Cost of alloy steel per kilogram is Malaysian ringgit 5. So these are the cost factors that affects the price. Direct material cost, fabrication cost, labor or workmanship cost, post-process treatment cost, and overhead cost. Our first case, forging iron crankshaft. So to get the direct material cost, we need to find the gross weight, which is equals to initial material weight plus material loss in process. To calculate initial material weight, we need the target mass over forging yield. Common range for forging yield is about 70 to 90%, and we would use the average, which is at 80%. right here. So the initial material weight is target mass 26 kilogram over forging yield 80, and we have a value of 32.5 kilogram. The material loss will be considered in three different situations: low end estimate, high end estimate, and average estimation. We would choose the average estimation, which is about 20% material loss and average forging yield at 80%. So we get a final value for material loss, which is 6.5. To get the final, we would have to sum up the initial material weight and the average material loss estimation, which is 40 kilogram, and we take that value and multiply it with the material price per kilogram, which leaves us at direct material cost of 240 Malaysian ringgit. So to estimate forging die fabrication costs, we take internet reference forging die, which is about 3,000 to 5,000, and we take the average at 4,000 Malaysian ringgit per hour and multiply the estimated average value in between 10 to 15% and add this value to the overall cost. We get a die cost about Malaysian ringgit 500. And for labor cost, we take the total process time per piece and multiply it with labor rate per hour. The time taken is the sum of time for forge one crankshaft and for post treatment, which is about 8 hours and 48. We add the values up and multiply it with the labor rate per hour. This value is based on internet reference, so we get a value of labor cost at 1,300 Malaysian ringgit. For post-forging treatment costs, we choose the main processes, surface and heat treatment, 16 to 40 per kilogram. So the average value will be taken at 28 multiplied by the target mass, which leaves us about 728. The machining is calculated by per piece, so we get an average value of Malaysian ringgit 190. The ultrasonic is a very precise operation, and we will use the high-end estimation for crankshaft, as crankshaft needs to be very precisely manufactured, so we take a value of 400. So the total process will be about 1,318, and we would use the same allocation from a die cost 12.5, and we get a allocation of 165 Malaysian ringgit. So the overhead cost comprises utility and facility rent. So utilities are electricity based on TNB data. We estimate them at 600 ringgit, and water rate would be at 403. The facility rent, we assume the factory is in Penang mainland. So based on data from MEDA, we managed to calculate an estimated rental price at 20,695 Malaysian ringgit. So we add up the total overhead costs and we get a 21,000 sum. For the overhead allocation rate, we take the total overhead divided by the total labor hours, and we get a value at 390 Malaysian ringgit. The table here shows the total cost estimation for forging iron crankshaft. Our second case, casting steel crankshaft. So the direct material cost for the gross weight, we would assume the same as scenario 1 multiplied with 5 ringgit for the cost of alloy per kilogram. We have 200 for direct material cost. For casting mold, we have 40 to 80 per kilogram. As average, we take Malaysian ringgit 60, and for the location, we choose 12.5% from the molding cost to be added into total costing. So we multiply the average value to the target mass and the location. We estimate the mold cost about 195 Malaysian ringgit. For the labor cost is the same as scenario 1, except for the molding cool down period and the process treatment. So time taken for one crankshaft is at 4 hours. Time taken to cool down each material is about 24, but not to be included into labor cost, but to be included into process time. Time taken for post treatment is at 48 hours. The labor rate is at 30. So we get a final value of 1,560 for the final labor rate per hour. So for post cast treatment, We choose the main processes such as surface heat treatment, which is about 390 per piece. Non-destructive testing takes 4 Malaysian ringgit per unit, and surface coating, which is a spray paint process for final heat resistant and anti-rust, which is about 35 to 45 per piece. We average it at 40 ringgit. So the total will be 434 Malaysian ringgit, and we would apply 12.5 allocation to this post-cost treatment, which is about 55 Malaysian ringgit. For the overhead cost, we would assume it to be the same as scenario 1. This would be the total manufacturing cost for casting alloy steel crankshaft. Thank you.